Hello and welcome to week 10. This is Wednesday's lecture covering chapter 24, the first three sections of chapter 24, Electromagnetic Waves. So please note we're not going to be discussing a lot of the things in this chapter. I really just want to talk enough about chapter 24 so that you see the beautiful symmetry of all the equations that govern electricity and magnetism, and to give us enough information to talk about optics. And optics is the last section covered on your MCAT review if you look at the beginning of the textbook. Okay, so I'd like to start out our discussion of electromagnetic waves by asking you a true-false question. Is the line integral of B dot dl equal to mu naught I enclosed? Right? Is it true that if I sum up all of the magnetic field contributions along this length, along this loop, will it equal to the permeability of free space times the current that goes through any surface bounded by this loop? And perhaps you'll say, well, yeah, of course it's true. That's Ampere's law. It's in my physics textbook. It must be true. Well, if it is, then explain this situation. Let's say you just hook up a generator to a capacitor and you send some current through it. And now you consider one surface, this blue surface, that you look at the current that's going through the blue surface, it's I. So B 2 pi r equals mu naught I, no problem. We've already done that. That's the magnetic field around a wire. But let's consider this tan surface now. How much current is going through this tan surface? The answer is none, because there's just empty space between these capacitor plates, so there's no enclosed current in that surface. That gives me a B dot dl equals 0. So I have a contradiction here. They both can't be true, and therefore Ampere's law is not true in all circumstances. Forgive me, that's white lie number 357. We're filling in these gaps now, right? I told you we would fill in these gaps once we had the whole picture. We're so close to having the whole picture for E and M. So Maxwell realized this contradiction, and he said there's got to be a current going through the gap. It's called the displacement current, and it has this value, epsilon naught, which is the permittivity of free space, times the time rate of change of the electric flux. And he presented a beautiful argument saying this is really the only self-consistent answer that ties all the equations of electricity and magnetism together, which is true. But I like to think, what would I have done if I were around in 1840 and I knew that the current through capacitor was CdV/dt, and I knew that the voltage in a constant field was just the value of the electric field times the distance between your voltage probes. So we know V equals Ed and I equals CdV/dt. Let's put those together. Make this substitution for V. Instead of dV/dt, I have dEd/dt. And also I know that the capacitance of a parallel plate capacitor is the permittivity of free space times the area of the plate divided by the distance between them. So if I make that substitution as well, and I cancel out some stuff, I get exactly the same relationship that Maxwell derived. I love doing this because hopefully it would help you see that if you had been around at that time, you could put these two simple ideas together, and you too could have come up with an expression for displacement current, and then all the laws of electricity and magnetism would have had your name instead of Maxwell's name. So this together with the Lorentz force laws are all of the equations that govern electricity and magnetism. So it's the pillars of E and M, these four equations. And so you know them by other names. E dot dA is Gauss's law, and B dot dA equals 0. We haven't given that a name. That's just saying that, well, there's no equivalent to a single charge for magnetic fields. There's no magnetic monopoles. And we did a problem like this where you found the total magnetic flux through a cube is equal to 0. And then we have E dot dl equals minus d phi dt. You'll recognize that as Faraday's law. There's no extra term here, right? And then this last one is Ampere's law with this little addition that Maxwell gave us. So you recognize B dot dl equals mu naught I, where I is the conduction current, as in through the wire, plus this other current, which is a displacement current. And then I wrote, and let there be light, because it turns out that if you manipulate these equations, especially if you look at the situation where we're just in a vacuum, so that there's no charge. If there's no charge, then E dot dA and B dot dA completely symmetrical. In a situation where we're in empty space, there's no conduction current. Then E dot dl equals the time rate of change of magnetic flux is very similar, in fact exactly symmetrical to B dot dl equals mu naught E naught times the time rate of change of the electric flux. So you see the symmetry between these equations now, especially in the absence of matter. They're exactly the same, except for these constants, mu naught, epsilon naught. So Maxwell realized that, and he, yeah, I'm sorry, I know this is kind of scary, but bear with me. We're just going to derive the wave equation because you'll see that it's similar in form to what we did in chapter 13. And if it's similar in form to what we had in chapter 13, the solutions for the equation must be similar in form. The only thing we're going to change is, instead of the maximum amplitude being some displacement in meters for a mechanical wave, we're going to say that the maximum amplitude is a value of electric field or a value of magnetic field. So I wanted to show you this animation of an electromagnetic wave. So it turns out we don't need a medium, and I think hopefully I convinced you of that by just looking at Maxwell's equations. We don't need a medium for an electric field and a magnetic field to exist in space. And this is an example of a plane wave where the electric field and the magnetic field, this is another symbol for magnetic field except it's magnetic field and matter, are perpendicular to one another, and they propagate in the direction given by the cross product. So if you were to put your fingers in the direction of E and then sweep them in the direction of H, your thumb would be into the page, or going to the right in this case. So that's the direction of propagation of this wave, is E cross B, and we're going to use that result a little bit later. The other thing I'd like to do is just freeze this at one instant in time. You'll notice that the electric field has some value. It's close to its maximum value in the minus, let's say this is the x direction, this is the y direction, in the minus x hat direction. And the magnetic field is close to its maximum value in the minus y direction. And then at a different point in time, we see now that the electric field has changed the side of its axis. Now it's on the positive x side, and the magnetic field is on the positive y side. So if we were just to look at a point on this surface where the plane wave intersects this plane, we'll see that the electric field is oscillating up and down like this, just like it did for our simple harmonic motion. Okay. So for a wave traveling in the x direction, we'll say that the electric field is going in the y and the magnetic field is going in the b. I'm going to use Faraday's law, and now we're just going to look at this in 2 dimensions. So now the magnetic field is coming out of the board, and I'm just looking at the xy plane, and my E dot dl loop is going to be this rectangle that you see. And in order to follow the right-hand rule convention, I need to go counterclockwise around this loop, because then my thumb will point in the direction of the magnetic field, which is pointing out. And since I know that this line integral is equal to d phi dt, first I'm going to do the line integral. I look at, for example, in this case, I'm going counterclockwise. So E is going this direction, but I'm going counterclockwise around the loop, which means E dot dl has a minus sign. So this is just E of x times the length, E of x times the length with a minus sign. And then on these two sides, I have E is perpendicular to my dl vector, and you know that the dot product of 2 perpendicular vectors is 0, so there's no contribution from this length. And then I have this final length, which is the magnitude of the electric field a little farther along the x-axis. It's a distance dx farther along the x-axis times this length L. So when I add that all up, I just get this, which you'll notice is very similar to the definition of derivative. We're just missing this dx term. So if I multiply this by dx, I have the definition of a derivative. And one of the things that I think makes this derivation confusing is that for this Faraday's law equation, we're looking at how the electric field is varying with position at one instant in time. If I go back to the animation, at one instant in time, I'm looking at how magnetic field is changing in this direction. How is the magnetic field changing in opposite the direction of propagation. I guess it should be in the direction of propagation in this case. But it's just one snapshot of time. So I'm keeping time constant for E while looking at the time rate of change of B. Okay, so in this case, if I were to look, you're already familiar with this notation, right? This rounded out D means a partial derivative. I'm taking the partial derivative of E with respect to x, keeping time constant. If I were to take the full derivative, I'd have to go the partial of E with respect to x times dx plus the partial of E with respect to time times dt. Okay. I think you've seen this in your chemistry class, and if you haven't, please let me know and I can talk more about it. But that's a partial derivative. So E dot dl equals L times the partial derivative of E with respect to x times dx. Now let's look at the right-hand side, trying to figure out the magnetic flux through this square at one instant in time. It's equal to the value of the magnetic flux times the area. Well, the area is just this length times width. So BL dx is the magnetic flux, and I take the things that aren't changing with time out of the integral, and I'm just left with L dx partial of B with respect to t. And those things are equal with a minus sign according to Faraday's law. So if I plug that into Faraday's law, I get this expression that relates the space derivative of the electric field with the time derivative of the magnetic field. Okay, we're almost done. We're going to do the same thing now for Ampere's law, except we're going to look at this at one instant in space. So here we're going to be keeping this, keeping time constant. We're looking at integrating this B dot dl integral and looking at the time rate of change of the electric flux coming out of this loop. So it's exactly the same as I did before. I'm going to go counterclockwise around this loop. Now this B dot dl is positive on this side, and B at some x plus delta x is going to be negative. So I have the opposite of what I created up there, but that's still the partial derivative of B with respect to x. Now I've got a minus sign because of the counterclockwise direction of the current loop. And now if I plug these into Ampere's law, I get this expression that relates the time rate of change of electric field to the spatial change of the magnetic field. So in the double box 1 and double box 2, if you put those together and take the first derivative of this with respect to x, and then you just plug in 2 for your partial B with respect to x, you get this, which is a wave equation. Right? This was, going back to chapter 13, it might be useful to look at your chapter 13 notes again. You'll remember that we got this wave equation for mechanical wave, where whatever is in front of the second derivative of the time term was 1 over v squared. Well, the stuff that's in front in this case is the permeability of free space and the permittivity of free space. So that means, I know this is hard to see, but this means that our velocity is 1 over the square root of mu naught and epsilon naught. And this was kind of a big moment in the history of physics, because if you plug this into your calculator, 4 pi times 10 to the minus 7th, and epsilon naught, which is 8.854 times 10 to the minus 12, you multiply those together, you take the square root and you flip it upside down, you'll get this number. Three times 10 to the 8th meters per second, which people knew at the time was the speed of light in vacuum. So Maxwell was like, aha, this is no coincidence. This is a wave, and its velocity is equal to the speed of light. Therefore, electromagnetic waves are light, or light is an electromagnetic wave. That was a big deal. We didn't know that, right? Now we know. That's why we put "and let there be light" after Maxwell's equations, because this is electromagnetic radiation is light. Alright, so now I just want to review a few things from chapter 13. You already know these relationships. You know the relationship between velocity, wavelength, and frequency. V equals wavelength times frequency. But now, for the things that we're going to be doing for the next 3 weeks, we're going to be dealing with light, whose velocity is the speed of light. So instead of V, we're going to use the symbol C for the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. It's the universal speed limit. and we know that the period is equal to 1 over frequency. The angular frequency is related to cycles per second with this conversion factor of 2 pi. So angular frequency equals 2 pi times regular frequency. And this wave number k is just 2 pi over the wavelength. It's an inverse wavelength. And we're going to put these together and use the form of the wave equation that we had in chapter 13. Instead of y equals some maximum amplitude sine kx minus omega t, I'm just going to use electric field, and the same thing for the magnetic field. And we have our full description of an electromagnetic plane wave. So here's an example from the text. Given that an electromagnetic wave with frequency 40 megahertz travels in the x direction, let's find the wavelength and the period. Well, I know that c equals wavelength times frequency, so I can solve this for wavelength to get wavelength equals velocity, which is speed of light, divided by frequency. So plugging in the speed of light divided by my hertz gives me a wavelength of 7.5 meters. So 40 megahertz, you might recognize this. This is AM. But if you want to, oh wait, sorry, no, that's not right. It's FM. This is the FM. Not even. It's close to citizens band. Disregard. Yeah, FM starts around 89 megahertz, and 50 megahertz is the citizens band wavelength. So if you wanted to make a full wave antenna that you were able to talk to your friends on your citizens band radio, it would be 7.5 meters long. Turns out we don't need an antenna that's quite that long. We can use a quarter wave antenna, which is what you'll see on top of police cars. Okay, and then the period is just 1 over frequency, so I just divide, take the reciprocal of frequency, and I get 25 nanoseconds. The second part of the question says we're going to find the magnetic field when the electric field has some maximum amplitude in the y direction. For one thing, I know that the direction of B, it has to be perpendicular to y. So if it travels, if our direction of propagation is in the x direction, then the magnetic field has to be in the z direction, because E cross B, right, y cross z gives me the x hat. Try it with the right-hand rule and see if you agree. Okay, now we're going to use the equation 1 up here, so this relationship between the spatial derivative of E and the time derivative of B, to just take the first derivative with respect to x of our equation for the electric field. Here's the electric field, right? It's sine kx minus omega t. If I take the derivative of that with respect to x, I get k e cosine kx omega t. I use chain rule. I just have to take the derivative of what's inside, and the derivative of what's inside with respect to x is just k. And if I do the same thing with the spatial derivative of the magnetic field, now when I take, the time derivative of the magnetic field, when I take the derivative of sine kx minus omega t, now I have to bring this minus omega out in front because the derivative of the argument of the cosine is minus omega. So that gives me minus a minus, and I get ke equals omega b. So the ratio between the electric field and the magnetic field, the maximum amplitude of the electric field and magnetic field, is omega over k. What's interesting is because the electric field is just E naught sine kx omega t, and B is the same thing, that means the electric field and the magnetic field are always related to each other by this ratio of omega over k. So I could have just as easily written E over B equals C. That's always true. And hopefully you'll recognize that as a velocity selector. It's exactly the same expression as we got for the velocity selector. Okay, yeah, I think I talked about that already. Oh, that's it. Okay, so for the homework today, I'm asking you to do 1 or 2 calculations for the displacement current, and just look. I'm not going to ask you to reproduce this on a test, but I do want you to look at it long enough to say, oh yeah, I could do that if I really needed to. So there's one question on the homework where I ask you to do some time derivatives to convince yourself that the wave equation is actually true, that it's actually a thing. And then finally we're going to be using this, the speed of light, 3 times 10 to the 8th, to hone our physics intuition about how long it takes light to travel from various spaces. Please don't hesitate to text or email if you have any questions at all about the homework, and I will see you on Friday.